Okay, welcome to this video on atomic structure, mass and the isotopes, looking to do a roundup of the exam questions that I've set for you over lesson 1. So straight in, looking at this first exam question, and I'm just going to highlight as I read. The figure below is a diagram of an alpha particle and a helium atom. So we've got our alpha particle here, we've got our helium atom here. What is the approximate size of the helium atom? So that's this one, not this one. So the answer for this is 1 times 10 to the minus 10. And you may remember from previous videos that I've done for you that we discussed the size of a nucleus and then the size of the atom. Now the size of the atom, as I've said here, is 1 times 10 to the minus 10, whereas the size of the nucleus, which is smaller, is 1 times 10 to the minus 14. So you do need to bear those values in mind. So just scrolling down. Question B, a helium atom is much larger than an alpha particle. Give one other difference between a helium atom and an alpha particle. So we're looking for a difference to the size. So we're looking between a helium atom and an alpha particle. So you can look back up at the diagram here. There's one really obvious one that stands out, and that is this one here, okay? But actually the helium atom has 2 electrons. And that is the answer that the mark scheme allowed, okay? That a helium atom has 2 electrons. So He atom has 2 electrons. Now in the mark scheme, 2 electrons was underlined. That means you have to have said 2 electrons. You can't just say has more electrons. You have to have said 2 electrons. The mark scheme also allowed you to have more mass, which I think is quite generous, but it allowed it, okay, because it's got additional electrons. Now, although the electrons are very, very small, they do have mass, so it allowed you to have more mass, or it allowed you to say that the helium atom is not charged. And the reason for that, obviously, is, if I scroll back up, an alpha particle is charged because you've got 2 protons, which are positive, 2 neutrons, but no electrons to cancel it out. Whereas a helium atom, you've got your 2 protons, but you've also got your 2 electrons as well. So that 2 positives would be cancelled out by the 2 negatives. And then this question here, what is the atomic number of the helium atom in the figure above? So again, really straightforward. We've got 2 protons in the centre there, so that means our atomic number is 2. Okay, protons tells us what element it is, but if our atomic number is 2, that means that it is our helium atom. Okay, on to this next question here. So we can see 3 marks are up for grabs. What is the charge on the helium atom in the figure above? Explain your answer. So it's not enough just to say a charge, you need to explain your answer, the reason why that is the case. When we see explain, we need to say why. So, really simple, okay, and I've basically alluded to that in what I've just discussed with you there. What is the charge on the helium atom? There is no charge. The charge is 0, okay? So you can have one of 3 things that allow for this first bit. You could say the charge is neutral. You can say the charge is 0. Or you can say that there is no charge. Okay, all 3 things there mean the same thing. So that's your first mark. But as I said, we need to say the reason why. And the reason for that is that our protons are, and I write this shorthand, are positive, okay? And our electrons are negative. And again, writing that just shorthand there. And the third mark is to say that the number of protons is equal to the number of electrons. So equal numbers of protons and electrons. So that means that they would cancel each other out. So if you had 2 protons, then you have 2 electrons. Overall, that's going to give you a charge of 0. Hope that makes sense. So, just scrolling on to our next question here. So, according to modern measurements, here, the radius of an atom is about 1 times 10 to the minus 10. The radius of an atomic nucleus is about 1 times 10 to the minus 14. Show that these values fit with the nuclear model of the atom. So again, when we discussed this and when we looked at the development of the atom, we discussed the nuclear model, and the key thing is that these values came from that. And the real key thing you have to remember is that the difference between the radius of the atom and the radius of the atomic nuclei was 10,000, okay? So the radius of the atom is 10,000 times bigger than the radius of the nucleus. Now, without me writing out all the numbers here, we've got 1 times 10 to the minus 10. We've got 1 times 10 to the minus 14. So that means there would be 4 more zeros attached. So if we put 4 more zeros there and put the 1 in front, that tells us that there is a difference between those of 10,000. So very simply, we can tell that, that the radius of the atom here is 10 times bigger than the radius of the 10,000 times bigger than the radius of the nucleus, meaning that it fits with the nuclear model. And that's what you had to get across, guys. There was 2 marks that were up for grabs, and it is the radius of the atom is 10,000 times bigger. It's going to write over there. And then the second point that you had to make is that the nuclear model states that the atom has a tiny nucleus. Just going to put in brackets above nuclear model. And therefore that is consistent with the nuclear model, okay? So therefore data consistent with the nuclear model. And there's 2 marks up for grabs there. You'll notice that I'm tending to bullet point these answers. There's nothing wrong with doing that. I would tend to, if I was you, write that out in sentences as I am here as bullet points, but you don't necessarily have to put the bullet points there. You can just write them out as though with sentences without the connectives necessarily, if that helps you not to waffle. Okay, so C. In 1931, a scientist discovered there are hydrogen atoms with mass numbers of 2, as well as hydrogen atoms with mass numbers of 1. A year later, another scientist discovered neutrons. Explain why the discovery of neutrons could explain the presence of hydrogen atoms with different mass numbers. Okay, so here we've got to be able to talk about a little bit more info as to what this question's asking us and what info we know about isotopes. Okay, so when we look at the periodic table, you'll see hydrogen is like this. Okay, now following the rules that we've had previously, the bottom number tells you the number of protons. So we know hydrogen has 1 proton. And to work out the number of neutrons, we do the top number minus the bottom number. So that would give us 0 neutrons. 1 minus 1, 0 neutrons. So the hydrogen that we see on the periodic table consists of not having a neutron present. But as you can see here, there were some that were found with a mass number of 2. So if I write that out here, 2H1. So again, we've still got 1 proton because we've got our atomic number of 1. But what you'll notice is we've got a mass number of 2. So if we do 2, the mass number, minus the atomic number 1, it leaves behind 1. So that means there is 1 neutron present in those isotopes of hydrogen there. So the questions are asking, explain why the discovery of neutrons could explain the presence of hydrogen atoms with different mass numbers. So the first thing that we needed to note is that all atoms of hydrogen, so all hydrogen atoms contain 1 proton. That's how we know they're hydrogen, because they have 1 proton. Okay, that's the first bit that we need to note down. But then the second bit, as we can tell from this, is that some atoms of hydrogen have 2 neutrons. One have 1 neutron as well. So you can have 1 proton and a neutron, hence the mass number being 2 at the top for those ones there. And then for the final point you had to make, so protons, and you remember this from previous videos, protons and neutrons have the same mass, so proton having a mass of 1, neutron having a mass of 1 equals a 2 overall. And that's your 3 marks there, just for making those 3 points quite clear, that protons and neutrons have the same mass. Some atoms of hydrogen would have a neutron as well, and if you added that neutron to the proton, that would give you a mass of 2, saying why the mass number would be 2. Okay, just moving down onto this one here then, so on to D. So the question asks, how would the results of the experiment shown in figure 2 change if neutrons were used instead of alpha particles to bombard the thin sheet of gold? So this is the scattering experiment. You're going to talk about this quite a lot, potentially in chemistry and in physics in your exams, okay? So what we need to talk about here is firstly about our neutrons. So it said, how would the results of the experiment change if neutrons were used instead of alpha particles? So just to draw down here, just to remind you, an alpha particle is 2 protons and 2 neutrons. So an alpha particle has an overall charge of 2+. A neutron is a neutral, has a neutral charge and therefore has a charge of 0. Okay, so a neutron isn't charged, so therefore is not going to have an attraction to things, because it isn't a positive, it isn't a negative, therefore it won't attract. So the first thing that we need to state based on that, really simply, is that neutrons are not attracted or repelled by a positive nucleus. Okay, so remember in that experiment, we found out that the nucleus was positive, and we found that out because the alpha particle went towards it and then repelled away. So that allowed us to know, because the alpha particle was positive, that the nucleus would have to be positive as well. If we used the neutron, which is neutral, no charge, we would never have found that out, because it would have passed straight through. Okay, and on to the next part. The final mark, which you think is really straightforward, is really simple, and it's what I've just said there, that actually if there is no attraction or no repulsion, then the neutrons would pass straight through. They would all pass through the foil. Okay, so that's the 2 marks up for grabs there. If we use neutrons instead of alpha particles, the neutrons would have a neutral charge, therefore no attraction or repulsion would occur, and that means that the neutrons would pass straight through. Therefore, there would have been far less evidence gained from that experiment if that was the case. Okay, and just going on to this final question here. Now, in the this final question here. Right, so apologies. And an isotope of carbon can be shown as 13 mass number, 6 proton number. Figure 2 shows an incorrect diagram of the structure of 13,6. Okay, so this is the one that we're meant to be looking at, but it's incorrect. Explain, so remember, why again? Explain why the diagram of the atomic structure shown in figure 2 is incorrect. Give a reason for your answer. Now, there's 4 marks up for grabs here, so we need to talk about this and think about what's going on. So in terms of atomic structure and electron configuration, we know that in the first shell, there should only be 2 electrons. If I look here at the inner shell, I can clearly see that there are 3 electrons. So that's incorrect to begin with. So the first bit I need to put in, so the first answer here, first shell or inner shell should contain 2 electrons. So that's the first thing that I can see. So that's 1 mark taken care of straight away. Okay. And then the next one is if you look at the periodic table, you'll notice that carbon is in group 4. So that means that the outer shell here should contain 4 electrons. Okay. But this one doesn't. This one contains 5. So that's incorrect. So outer shell should contain 4 electrons. And again, that's because carbon is in group 4. So that's the second mark. Or what you could have said as a different one to that, okay, which makes the same point, is that overall there should be, oh, apologies, press the wrong button there. There should be 6 electrons, and there aren't. So if you look at the diagram, you've got 3 in the middle, 5 around the outside. That's 8 electrons, which is incorrect for our atomic number that we can see here. And our third mark is if you look at the number of protons in that nucleus, 1, 2, 3, 4, 5, well, we know the atomic number, the proton number is 6. So therefore, there should be 6 protons, or 1 more proton. Okay, so that's the third mark. The final mark is once we've understood that there should be 6 protons, if we then count up the number of neutrons we've got here, so we've got 1, 2, 3, 4, 5, 6, 7, 8. Well, actually, if we had 6 protons, which we should have, and then we added 8 neutrons on top of that, that would mean that we would have 14 carbon 6. And that's incorrect. So the final mark, the fourth mark there, should be that there should be 1 less neutron. And that's your fourth mark up for grabs there. Okay. I hope that's been useful. If you've got any questions, pop them in the comments below. I hope you're well and work hard. Thank you.